This is section 1.7, linear independent. After linear combination and span, this is the most important concept that you'll learn this semester. In this paragraph here, I have two equations, a matrix equation and the corresponding vector equation. Now, this is a homogeneous system, and so we know that one solution will be the trivial solution, x1 equals x2 equals x3 equals 0. The question is, are there non-trivial solutions? If there are, we would say these vectors are not linearly independent, hence they're linearly dependent. If there are no non-trivial solutions, then we would say these vectors are linearly independent. So here's the definition in this box, and you do need to memorize this. A set of vectors is linearly independent if the only solution, that's the important part, to this linear combination is the trivial solution. And the trivial solution is all the x's are 0. Now you could use c's, c sub i's, instead of x's, but I'm using x's so that it looks more like a linear system. And then if there is a non-trivial solution to this equation, we call that a dependence relation. So if you're looking for a dependence relation, you're looking for an equation that looks like this, where not all the x's are 0. And so we're going to find a dependence relation in this example here. We've got three vectors. We want to show that the set v1, v2, v3 is not linearly independent. And we're going to do that by finding a dependence relation. So we're trying to solve the system x1 v1 plus x2 v2 plus x3 v3 equals 0. So we know how to do that. We're going to augment with the 0 vector and we're going to reduce. So I suggest you pause the video here. Make sure you can reduce this matrix to reduced echelon form. All right, hopefully you did that. Let's just go through the steps. The next step here would be to take this 1 and kill off the 5. So I'm going to leave the top row alone, leave the second row alone. I'm going to take the top row, multiply by -5 and add it to the last row, and that'll give me -1 and then 18 and then 0. And then I can use the second row to kill the third row completely, multiply the second row by -1 and add it to the third row, and that gives me 1, 2, -3, 0, 0, -1, 18, 0, and then all zeros on the bottom. And then I can use this -1 to kill off the 2 above. So if I use that -1 to kill off the 2 above, then my top row becomes 1, 0, 33, 0. And then as I write down this second row, I'm going to go ahead and multiply through by -1. So this is a 1, and that's a -18. That's a 0, and then everything else is 0. Okay, I'm in reduced echelon form, so I can read off the solution. X3 is free, that's t. X2 is 18t, and x1 is -33t. Now, that's infinitely many solutions to this equation. I just need one solution. So I'm going to let t equal 1, and then I get x3 is 1, x2 is 18, and x1 is -33. Okay, so I'm not done. I wouldn't want to leave my answer like that because I was asked to write down a dependence relation. So my dependence relation is this equation here, where I'm going to replace the x's with -33, 18, and 1 respectively. So I'm going to get -33 v1, because that's the name of the first vector, plus 18 v2 plus v3 equals 0. That's my dependence relation. Nothing special about t equal 1. I could have let t equal 2, 3, 4, anything except 0. Okay, write that as a matrix equation. Okay, so I'm going to copy down the matrix A, which is v1, v2, v3 as the columns. So 1, 3, 5, 2, 5, 9, -3, 9, 3. If I multiply by the vector -33, 18, 1, I'm going to get 0, which is the 0 vector. So matrix equation, vector equation. All right, here's another one. Let C1, C2, C3 denote the columns of this matrix here. And suppose we're given that the first column, C1, plus twice the second, 2C2, is equal to the third. Find a non-trivial solution to AX equals 0. Okay, so let's rewrite this as C1 plus 2C2 minus C3 equals 0. and C's are the columns. So my non-trivial solution is going to be the weights in this equation. X bar will be 1, 2, -1. It's my non-trivial solution. And just to spell that out for you, the reason why that's true is that if I take this matrix A, 4, -7, 9, 1, 5, -3, 6, 3, 3, and I multiply by the vector 1, 2, -1, I'm going to get 0, 0, 0. All right, big theorem, theorem 1.7. I named this myself. This is not theorem 1.7 in your book. I don't think there is a theorem 1.7. I'm just combining some important facts. Let A be an m by n matrix. The following are equivalent. The columns of A are linearly independent. AX equals 0 has only the trivial solution. That's just translating the definition of linearly independent to a matrix equation. And that's equivalent to A has a pivot in every column. And the reason for that is you want no free variables in the equation AX equals 0. Now, we've got a lot of information about pivots. So at the end of these lecture notes, I have a summary of the important facts regarding pivots. So we'll talk about that when we get there. How many pivot columns must a 5 by 7 matrix have if the columns are linearly independent? Well, according to this theorem, 5. There are 5 columns. We need a pivot in every column. Okay, how many pivot columns must a 2 by 3 have if its columns span R2? Now, we have to go back to theorem 4. Theorem 4, the columns are going to span R2 if and only if we have a pivot in every row. So by theorem 4, you need a pivot in every row. Okay, there are 2 rows. That means, so, and here's a little comment here. If this is a pivot position, which it is, then the row it's in is a pivot row, but that also corresponds to the column it's in. You have a pivot column. So if you need 2 pivot rows, that means you're going to need 2 pivot columns. Okay, for what H is the set V1, V2, V3 linearly dependent? So according to the theorem above, if I put those 3 vectors into a matrix and call it A, which I did right here, if those vectors are linearly dependent, I'm going to need less than 3 pivots. Need less than 3 pivots in A, which is this matrix. Because if I have 3 pivots, then the columns will be linearly independent. I want to know for which H they're linearly dependent. So I went ahead and started reducing the matrix A, and getting to this point here, there's only one more reduction I need to do. I'm going to leave the top row alone. You should make sure you can follow those reductions. 0, 1, 0. I'm going to add the second row to the third. 0, 0, H plus 4. Now that's echelon form. When you're answering questions about pivots, you can stop at echelon form. So stop here to look for pivots, because you don't need reduced echelon pivots. Can't talk and spell at the same time. You don't need reduced echelon form to see pivots. You only need echelon form. So why go all the way when you can stop here and say, okay, I'm looking for 3, well, I want less than 3 pivots. So I've got a pivot here, I've got a pivot here. If I want less than 3 pivots, I need H equal -4, because I'm looking for dependence. Okay, so pause the video and do this one. Answer the same question except with these 3 vectors. Okay, hopefully you ended up with all H. I'll just take you through the steps there. 1, -3, 2, -3, 9, -6, 5, -7, H. Okay, and now I'm going to do 2 row operations at once. I'm going to take the 1 and kill the -3. So I'll take the top row, multiply by 3, and add it to the second row. I get 0, 0, 8. And then I'm going to take the top row, multiply by -2, and add it to the third row to get 0, 0, H minus 10. Okay, if we think of this as the matrix A in the equation AX equals 0, we can see that X2 is going to be free regardless of what H is. So if H is 10, great. If H is not 10, great. X2 is still going to be free. So we're going to have a free variable in AX equals 0 for all values of H. So for all values of h, those three vectors are linearly dependent. 4 special cases regarding linear independence and dependence. So as these examples above illustrate, when you've got vectors, let's say 3 vectors in R3, it's usually not obvious if they're linearly independent or linearly dependent. You usually have to do a matrix reduction to answer that question. So you can't just stare at them and say, oh, I know the answer. There are 4 exceptions to that. And these are the 4 exceptions where you can just look at the set and say, I know the answer. So here are the exceptions. If you have one vector, a set of one vector, and it's non-zero, then it's linearly independent. Here's why. Suppose we have x1, v1, and that's equal to 0, and we're told v1 is not 0. Well, the only solution to that is x1 equals 0. That's a trivial solution. So by definition, that vector is linearly independent. A set of 2 vectors is linearly independent if and only if one is not a multiple, 2 non-zero vectors, one is not a multiple of the other. And this only works for 2. You can't do it for 3. So suppose we have 2 vectors, v1 and v2, and suppose v1 is twice v2. So it's a multiple of v2. Here's why this set would be dependent. So if that's true, then here's a dependence relation. v1 minus 2v2 equals 0 is a dependence relation. I won't be able to do that if v1 is not a multiple of v2, okay? Third one, any set with the 0 vector is linearly dependent. Here's the proof, because it's super easy. Relabel the vectors. So suppose v2 is 0. Start calling that v1. Just relabel them. You're allowed to do that. Here's a dependence relation. So v1, is the 0 vector. So 1 v1, and then I'm going to take all the other weights to be 0. 0 v2 plus ... 0 vp equals 0 is a dependence relation. For a dependence relation, you only need one of the weights, the xi's, to be non-zero. They can't all be 0, but if one is non-zero, that's good enough. So here I've taken one of them to be non-zero, and it doesn't do any harm because I know this is the v1 is the 0 vector, and then I kill off everything else. All right, and then finally, a set with more vectors than there are entries in each vector is linearly dependent. So this is theorem 8 in your book, and it's stated like this. A set of p vectors in Rn is linearly dependent if p is greater than n. That's a little confusing. I think in English it's a little easier to understand, and I think it's even easier to understand if you look at an example. Here's 3 vectors in R2. 3 vectors in R2. So I have more vectors than there are entries in each vector. In order for this set to be linearly independent, I would need a pivot in every column. There's no way I could have a pivot in every column because there's only 2 rows. So can't have a pivot in all 3 columns since only 2 rows. Remember, if you're a pivot column, you're also a pivot row. And so the maximum number of pivots you could have is 2 because the maximum number of rows is 2. So you could only have 2 pivot columns. Thus, these columns cannot be linearly independent. All right, so let's just do a fun practice problem here where we look at 4 different sets and we state whether or not they're linearly independent, Li, or linearly dependent, LD, and we justify it using one of those numbers above. So for the first one, I've got 2 vectors. So I want to be looking at special case number 2, which talks about a set of 2 non-zero vectors. So it's going to be linearly independent if and only if neither vector is a multiple of the other. Well, for this to be a multiple, it's looking good because 9 is 3 times 3 and 6 is 3 times 2, but 4 is not 3 times 1. So those are linearly independent by number 2 because v1 is not a multiple of v2 if I call this v1 and that v2. Okay, next one, the columns of this matrix. Well, there are 4 columns, but there's only 3 entries in each column. So those are linearly dependent by number 4, since I have 4 vectors in R3. Next one, that's a giveaway. That's dependent That's number 3. One of the vectors is the 0 vector, so automatically linearly dependent. And then D is going to be linearly independent because I have a non-zero vector and there's only one of them. So that's by number 1. All right, and I want to finish up here, we'll almost finish up, with the characterization of linearly dependent sets. And this is an easier version than the one in your book. A set of vectors is linearly dependent if and only if at least one of the vectors can be written as a linear combination of the others. At least one, but not all necessarily. So this example here is to illustrate that not all of them have to be linear combinations of the others. So let's call this V1, V2, and V3, and let's graph those. Here's V1, here's V2. V2 is a multiple of V1, and V3 is up here, okay? I can write V2 as a linear combination of V1 and V3. Here it goes. V2 is 2V1 plus 0 V3. Thus, this set is linearly dependent. But I want to illustrate, I can't write V3 as a linear combination of V1 and V2. But V3 is not equal to A V1 plus B V2 for any A or B, because the second entry in V3 is 1, but the second entry in V1 and V2 is 0. So there's no way I'm going to get a non-zero number in the second entry by taking a linear combination of V1 and V2. Okay, and here I want to end it with just a recap of what we have so far in terms of pivots. So when we're looking at AX equal B being consistent for all B, we want to be looking for pivots in every row. The reason for that is when we take A and augment it with B in the last column, we don't want to end up with all zeros and then something non-zero, like 5. That would be bad. That can't happen if A has a pivot in every row. Remember, A is the coefficient matrix. And then pivots in every column, that's testing for linear independence. So AX equals 0 has the trivial solution if and only if A has a pivot in every column. That's so that AX equals 0 has no free variables. So it's a lot to keep straight. I suggest you memorize both of these theorems. Even if you're not quite understanding it yet, the first step is memorize, then you can start to work on understanding. I know it seems counterintuitive. You would think, oh, I have to understand it before I can memorize it. Sometimes in math, it goes the other way around. All right, and that is the end of this section.